Hello, this is Concrete Path. Today's lecture is about the shear stresses in beams. So this topic is that you have a shear stresses in beams. Shear stresses in beams. So you have some beam, you take some beam. Let's say this is some beam. We have the dimensions of BD, L, and you have some support, simply support beam. Let's go to some point at a distance of x. You take some point anywhere, because our civil engineering is all about your statics. We don't want acceleration of the structure, so we say that each and every point in the structure that should be in equilibrium. So if you take any point outside from the material, and that should be in equilibrium, in the force equilibrium, and that should be in moment equilibrium also. So if you take that point, any point, let's take any point A. Let's call this point as point A. So there would be some neutral axis also. There would be some neutral axis also because of that loading. If you take some loading, so this is some neutral axis. Then we can say you go to some point A at a distance of y, and you would say what's happening on this point A. So you take that point between two sections. One section that is let's call this section as XX section, and after that you take some differential element dx, and after that there's one more element, one more section that is YY section, and you want to say what's happening on this point. What is the effect of this one? What is the effect of this element, this area on that particular point A? So if you take that elemental area, I would say that area of that beam. So this area would be, if you take this one, the element formed here would be some sort of cuboid. Some sort of cuboid would be there. So this one, some sort of cuboid would be this one. I would call this as an element, and an element of the beam. So this we have dimensions of dx, and along the z direction we have dimensions of width b, and in the depth we have, let's say total depth is d. Let's say total depth is d. Then we can have this one. This depth is equals to d by 2 minus y, because neutral axis is at the centroidal axis, so we'd say d by 2 minus y. So this is point A. Let's say this is the point A. Now we want to say what's happening on this point. There should be equilibrium of forces on this element. Now if you want to say how the forces have came here. Let's take example of simply support beam with the point load at the midspan. We have the bending moment diagram as this PL by 4. We have the reaction of P by 2 and P by 2 reaction. If you take now at X from one of the supports, you take one cross section, XX cross section. After that you take YY cross section. This is your DX element. You would say what is the moments here? Let's say the moments here would be equals to P by 2 of X, and here the moments would be P by 2 of X plus dx. Okay, so let's call this P by 2 of X equals to M, and similarly we would have M plus dm from this side. So you are applying on this differential element a moment of M from this side and M plus dm from the other side. So because of the moments we have from the flexural formulae, because of the bending moments, we have bending stresses. So because of the bending moment, we have sigma equals to my by I. So we would have these stresses, my by I. So we had this section we have from this section XX section, then we have from this side YY cross section. Let's say that we know that variation of these bending stresses would be in this way: compression and tension. In the top we have compressive stresses, and in the bottom we have tensile stresses. So if we make that, let's make that diagram here. So we have that stresses. Let's say that on this cross section we have compressive stresses, and on this side we have tensile stresses. So these are your tensile stresses on this cross section, and we have compressive stresses on this side. So similarly, from this side YY cross section, you're having those stresses of compressive, and here we have tensile. Now you took the element that's having those stresses in the form of compressive stresses. So this part we are taking. If we take this part, so we are left with in this way that you have some stress, compressive stresses in the XX cross section. There is some stress here also. So this is our stress variation here. So there is some stress variation. Both sides are we have compressive on the different cross sections. Let's call this as, let's say there is some net force in the XX direction, and there is some net force because of that YY cross section FYY. But because your stress is varying with the depth, so that means your force with depth, force with the depth varies. So you need to take that. You want to say what is the total force? For that you need to take a differential element. You need to take a differential element of that. So out of that total depth of d by 2 minus y, out of this total depth d by 2 minus y, you need to take differential element. Let's take a differential element. That was, so our point was at a distance of y from neutral axis. So let's take from the cross section a point A from at a distance of y from the neutral axis. So then after that we take some differential element. Let's call that differential element as dy. So the area of that differential element would be equals to, area cross section of that differential element would be equals to, I would call it small area of that cross section would be equals to small b times dy. Okay, b times dy. Now I would say that the stresses, the horizontal stresses would be acting on this smaller area of that cross section. So some stresses would be there. Some stresses, we know that's variation of the stresses in this way. So there will be some stresses on this differential element. There will be some sort of stresses. Let's call that stress as sigma. So I would say total small force acting. So I would say there is some small force acting. So let's say that small force acting from the x direction. So that is some small force of sigma into dA. Okay. Similarly, from the other side also FYY, because we have some stresses sigma into dA. We have some stresses sigma into dA. We have some stresses sigma into dA. Now, if we say that, now what is the value of sigma? We know that the value of sigma equals to m y by I dA. So for that you have to say what's the value of m from this x side. From this x section we have moment of m equals to p by 2 of x. So let's call it as m. So we have from this side m, value of that stress equals to my by I. And from the other side we have moment of m plus dm. Then we have y by I dA. Value of y is same, value of I is also same, value of dA is also same at that point A. So now we say that what is the total force in that XX cross section? So I would say total force in the XX cross section would be integral. So total force dfxx, integral it. So that would be give me total force in XX direction, or we can say total force in this direction acting on cross section XX. So that would be integral of my by I and dA. The value of dA was equals to that dA was equals to bdy. And your limits of that that the differential area you took, the limits were from some value of y to maximum it can go to the top, that's d by 2. So the limits are from y to d by 2, y from y to d by 2, y to d by 2. Similarly, so we got the total force in the horizontal. Similarly, if you want to take the total force in the YY, that would be equals to, that is in this opposite direction, that is equals to m plus dm y by I. That I is about neutral axis. then we have y, then we have small differential area, that's b dy. So same limits we have, y to d by 2. Now you would say that there's no external force acting here. You would say that summation of forces should be in the horizontal should be equals to 0, because we are dealing with the statics. So on this element that was at a distance of y from the neutral axis. Let's say this was some neutral axis. So this was point A at a distance of y from the neutral axis. So you said that this element should be in equilibrium because we are dealing with statics. So let's take that equilibrium of forces. I would say one of the forces was in this direction, that is fxx, plus fyy was in opposite direction. So I can call it, let's call this direction as positive. Let's call this direction as positive, or let's call this direction as positive. This direction as positive. So I would write it as positive, and this one write as negative. And I would solve how much force, what is the value of that net force? It should be equals to 0, but we want to say whether it is 0 or not. Let's say that the summation of forces. Let's write the summation of forces. I would say y by I b dy integral plus minus times m plus tm y by I b dy, and limits are same. We have the limits of y to d by 2, y to d by 2. Similarly, that we can say that we have the two terms that are common, and you can subtract those because they are the same values. We can subtract that. So we are left with that value of integral dm y b dy by I, limits from y to d by 2. So there is a net unbalanced force. So I would say that there is some net unbalanced force. So I would write that statement. So let's call this statement that bending, I would say moment की वजह से बेंडिंग मोमेंट की वजह से बेंडिंग फोर्सेस का अनबैलेंस हुआ. सो इस अनबैलेंस को बैलेंस करने के लिए there would be some hero. So hero comes here, that's called as horizontal shear force. Horizontal shear force. So horizontal shear force that has came here balance करने. So there is some hero coming here that's going to balance this force. Balance करने के लिए. Let's call that horizontal force as F shear. Let's call that horizontal force that F shear. So we know that net value of this forces is in this direction. So there should be some balancing force in the opposite direction. I will call that. Let's call that force as F shear. So I would say there should be some horizontal shear force acting on this element on this bottom surface, I would say. So there should be some force of F shear in the opposite direction such that it would balance the total force. So then I can write that summation of forces Fx plus Fy plus some force F shear, and that would be equals to 0. And finally I would say I will say that F shear equals to this one. And if I say that this shear force is acting as a shear stress along the bottom area, I would say this one is your area. This one is your area of dx into some width b, and there is some shear stress acting on this such that tau times b dx equals to some F shear. Tau times b dx. So I would call this as tau b dx. So if I write that equals to tau b dx, then I would do some calculations. I would do some tricks here. So if I write that dm by dx y b dy, then we have, so b gets cancelled. Is it going to cancel? b dy b dx. let's say that the area you had small differential area, that dA. Let's keep that dA as it is. So we had small differential area. If we keep that as it is, if we keep it as it is dA, if we keep it as it is dA, bdy, so bdy, let's keep it as a dA, small dA, as a small dA, as a small dA, so small dA, so small dA, we are going with that small dA, and we have some divide of b, and we have already y, then you integral it, so we got some tau value. So we got some tau value based on this calculation. Based on this, we got some value of tau, that integral dm by dx from limits y to d by 2, and we have y times dA IB. So we know that the change of bending moment with the variation in x, that gives you shear force. So the derivative of bending moment function gives you shear force. So we are provided with some shear force, that's transverse shear force, and we have some integral yda for the area above, that point A. Then we have I and B, where the B we took here, that was the dimensions of that differential area, that was because of that effect of the shear stresses that we took. So we took the shear stresses area here, we have shown the element, so some shear force was acting here, so and we said that this is acting for this bottom area. So the bottom area is having some width b, so same we have took here, that we have some width of b, so on that shear stress is acting, so some shear stress is acting. So this is the width of the cross section at just at the point where we are calculating the stresses. So we had this point A. Above that point where we are having the width of B, I would write that where your B is the width of, where the B is the width of cross section at the point A. Let's call it as point A, at point A, where you are calculating the shear stress, where shear stress is being calculating, where we are calculating the shear stresses. So we got this one. Now we know that integral yda, that's first moment of area. Let's have this as v a y bar by it ib. So we have this first moment of area that we call it as vq by ib. So this is your shear stress area. So if you say that you had some loading of that p, and we want to say that at some x, what was the shear force? I would say shear force would have been p by 2. I would say shear force would have been some value of p by 2, Then after that we had some shear force of again p by 2. Had it been because of has been this shear stress because of that transverse loading, we would have got the shear stress value of p by 2 of, let's say the cross section was B and D, so we would have got this shear stress p by 2 of BD. So that means that we got some different parameters here. We got some first moment of area. We got first moment of area here, first moment of area in the equation, and we got second moment of area in the equation, second moment of area also. So one is your yda, then next is your y square dA. So we got two areas. So where your q is the I would call it as where your q is the first moment of area. Let's say the area that was area above, above point A, about the first moment is about the neutral axis, because you took the y from the neutral axis, and there is some centroid of that particular area from the neutral axis, so that we can call as yc or y bar or yc, and you had some area dA, so we are calculating the first moment of area about the neutral axis. So that is your value of q. And next one is that value of I. The value of I is the second moment of area. That is the second moment of area. Second moment of area about the neutral axis. About the neutral axis. About the neutral axis. So we have that. One is your I. Next one is your Q. That's AY. Next one is your integral y square dA. This one is your y dA. We can say that this term, that first moment of area, it can be negative or positive. But first term, that's always positive. That's always positive. And this can be negative or positive. So we got the terms here. So let's write the equation now. Final equation where shear stresses in beams equals to some shear force at that cross section. What is the shear force at that cross section? What is the shear force at that cross section where you are? So we have this. Let's say we had a beam. We had some beam. So you take any point A at a distance of y from the neutral axis. So we know that at this point, we know that on this point there would be some shear force. Let's say the shear force would be some V, some shear force function of V. So I would say the shear force here is it's V. Based on the SFD. Based on the SFD, you can calculate the shear force on that particular section. Shear force V. And we have also that AY bar that we also call as Q. First moment of area about the neutral axis. First about neutral axis. So there we have some term Y that was from the neutral axis. After that we have first moment of area, that's about the neutral. That's second moment of area about the neutral axis. So that's say BDQ/12 for this rectangular section, BDQ/12. And we have then after that width, that's B. So this is the width of the cross section. Width of cross section at point A. What's the width of cross section at point A? Let's say you were calculating the you want to calculate the shear stresses at the point A. You would say, what does the cross section looks like? How is the cross section? And on that point, near that point, what is the width of that cross section? Width B. So that's the width B. So we got these parameters in the equation. Tau equals VA y bar by I IB. So we got this equation. So had it been, so let's say that there was a beam with the pure bending moment. So there was only a pure bending moment. So this is your simply support beam. Let's say, what's the bending moment diagram? That would be a constant M. This is your BMD diagram. So BMD. So the BMD is remains constant throughout the section. So then you want to say at particular point A, above the neutral axis, what is the value of what's the effect of that? I want to say, what is the that is there any balance? Is there any balance of the forces on that differential area above that point A? So this was neutral axis, and you took that element, you took that point A above neutral axis from by a distance of y, and this was your d/2 minus y. Then we said that there would be some moments developed here because of m, and here would be some moments m plus dm. But we know that there's no change in shear, there's no change in bending moment. There's no change in bending moment, so we'd say m from x side equals to m from y side. So your dm is equals to 0. And then after that, you would say some stresses would be there because of bending stresses. There would be some bending stresses because of some that bending moment. We have some bending stresses. Then I would calculate that my dA by I from this side, and same we have from the other side also. So I would subtract that. So we would get a value of 0. That means that there should be no shear force. There should be no shear force because there should be no shear force because there's no change in shear bending moment along x. So that was the governing equation of that SFD. Governing equation, dm by dx equals to shear force. So this is one more proof that you can show by that the change in shear bending moment gives you shear force. Change in bending moment gives you shear force. So that means shear force will develop only if there is change in bending moment. So let's write that. Our shear stresses in beams develop in beams only if there is change in bending moment. If there is change in bending moment. There is change in bending moment. So one more that this is one of the most important statement, that shear stress would develop only that if you have bending moment. We may have one more shear stress, that is indirect shear stress. That is different from this one. We have indirect shear stress that can be developed because of twisting moment, I would say. Next topic, that's torsion. That's torsion. We said that twisting moment. We have some shear stresses, but they are indirect shear stresses. We will solve that also. So we have that dm by dx equals to 0 because your m is not changing with the x. Because change in moment is 0. Change in moment is 0. Because change in moment is 0. Because change in moment is 0. So we got this one. So let's say that, let's take that now. So if we take that, so we have some variation of shear stresses. If you said that the shear stress variation should have been, we know that there is some shear force on that point. Let's say the shear force diagram was in this way for the point load, and you wanted to say what is the shear force at this x cross section, what is the shear force at that point on the cross section point A above neutral axis at a distance of y. I would say let's calculate the shear force here because of point load P at the midspan. I would say the shear force diagram is P by 2, and that it's P by 2. Then it's up to the mid, a constant value. Then after that, so I would say the shear force here on x is equals to P by 2. Then if you divide by that area, that it would give you a constant shear force diagram of shear stress diagram of P by 2 BD. So the shear stress equals to P by 2 BD. But if you analyze the actual shear stress distribution, that equals to that is some sort of parabolic nature because of that VQ by IT, VQ by IB, that is actual shear stresses. So we call the shear stress that V by BD. There is some shear force on the cross section, and we divide by area. We got some shear stress of, we call it the shear stress as tau average. That means because of the transverse loading, you had some beam, you applied some shear force, you applied some force. There to be at particular point there will be some shear force V, and you say what is the cross section? We would say V by then I would say shear stress equals to V by BD. So it is a constant function. It's a constant function, that V by BD. That is a shear stress. Shear stress is constant throughout that section depth of the cross section. But actual variation is not that same. So there would be some value of shear stress, that is we can call it as tau average. That's a notation that to represent that V by BD. Shear by area, we can say shear by area. That's tau average, we call it as tau average. So let's take now that. So we got that definition, that in the beam, because of bending, we had bending force. We had a bending force unbalance because of bending moment. Because of bending moment, we had some bending force unbalance. There came hero. Hero was your horizontal shear force, and thereby the shear force was equals to tau and width into that small dx. Then the shear stress developed equals to VQ by IT, VQ by IB. So we got the shear stresses. Now the thing is that you could solve that. We know that Q equals to AY, and I said that it is the first moment of area, that the area is above. The area should be above neutral axis. The area should be above neutral axis. About neutral axis. Moment should be about neutral axis, but area should be above. The area should be above that point A. The area above that point A. Then I can say that you can take area below also. If you had that point A, you can take the area from the cross section. You can take the area. We had two options. This is your point A along the cross section. You can take area 1, or you can take area 2. We can say area 1 y1. So there is some neutral axis. I would say this is some y1, or we can say we have to go to the y bar, up to the centroid of the area. We have to go to the centroid of the area. So centroid of area 1 would be somewhere here. So centroid 1, let's call that as that y1 bar. So you can go to up to a1 y1 bar, or you can go to a2 y2 bar. Let's say from the neutral axis there is some centroid, so you can go to a2 y2 bar also. That we can show also by that we know that first moment of area, we know that first moment of area of entire section that is 0 about neutral axis. So because your first moment of area, this can be negative or this can be positive. So if you take the overall first moment of area about the neutral axis of the entire section, that would be equals to 0. We want to say how that is possible. So this is the depth d and some width b. There's some neutral axis. So we know that neutral axis is the centroidal axis. If you say what is the total moment of area of that entire section about the neutral axis, I would say Q about the neutral axis. That would be area of BD, and the centroidal distance is that you have to go from the neutral axis to a distance of y, where the centroid is. We know that centroid is at the location of that centroidal axis itself or neutral axis itself. So I would say BD into 0. That means your first moment of area about the neutral axis is the 0. That's the definition of neutral axis also. That is the definition of neutral axis also. That one is that it has bending stress 0. Next one is that we have first moment of area also 0 here. First moment of area also 0 here. Now you had two areas. You could have solved that. Let's say that you wanted to find the shear stresses at a point A. At a point A that was from neutral axis at a distance of let's say the total distance was, let's say the total depth is 100 and width is also 100. So you are worried about that point that was 25 mm. The depth was 25 mm. So I would say that the top area that is equals to, so area 1 would be equals to 25 into 100. And area 2, that entire area that's below that point A, entire area that's 75 into 100. Can I say that? So that is 2500. And this one is your 7500. Now area is different, but I'd say that the first moment of area is the same. That's I said you can take a y1 bar or you can take a2 y2 bar. Let's check that. Let's verify that. So if you calculate a1 y1 bar, we had that a1 equals to 2500, and we know that centroidal axis would be at 50. This is centroidal axis, neutral axis. There is some centroid of the area 1. Let's say the centroid is here. So centroid 1, I would say y1 bar is at a distance of 25 plus 25 by 2. That is 37.5 mm. So 37.5. So we got the a1 y1 bar first. Now you want to say what is the area 2? We have the area 2 that is 7500, and we have, but actual thing is that you can take that separate. Let's say that, let's take that separate. So we have this area. We have this area of 75 total depth of 75, and the neutral axis at, this is 25. So neutral axis is here at a distance of 25. So width is total 100. So we want to say we have two different areas. Let's take the centroid of first area here. Let's take the centroid of second area here. Total area. Let's say that you took the y above positive and bottom you can take negative y, because y is a function, so it's with respect to that neutral axis. So above the neutral axis you can take positive, below the neutral axis you can take negative. So you take that centroid 1 that's at a distance of 25 by 2. So you can write first area is your 25 into 100, and the centroid is at 25 by 2. Then after that it is positive. After that you have next area that is 50 into 100, and the centroid is at, so this is total of 50. So centroid is at 25. So you can write minus 25. Because neutral axis, the point is below the neutral axis. So you can take minus 25. So you can also get this value of 2500 into 37.5. That's negative 37.5. You can take negative 37.5. Finally, you can, if you can add those two about the neutral axis, so you can get this value equals to this value. So you can add them, and finally you can get the first moment of area about the neutral axis equals to 0. So we got this one. Confusion clear that it's up to us now that whatever area and first moment of area you can take, that is easier for you. that is easier for you, you can take that one for your point A. Let's say the point A is here, and if the area is smaller, so you can take about top. If the area is bottom side area is some sort of big area, you can avoid that area. You can take the top area. And if the area is if you want to say below the point, it's if the section is such that you had this area I section and point was somewhere here, you can take this area bottom area, because this is easy to calculate. So you can take this area bottom area. Now we had some assumptions, but we had not discussed those in that shear stress calculations. So we write that assumptions in shear stresses derivation, assumptions in tau derivation, shear stresses. So when we took that element of that element between the cross section XX and cross section YY, we said that there is some shear force acting. So with that, shear stress was acting on the bottom area of B into dx, tau times B into dx. So we said that the shear stress is a constant function with the width. So we say that shear stress is a constant function of width. That means it does not vary with the width. We said that shear stress is constant along the width of the cross section. But actually, if you check the width, if you see the cross section, the shear stress distribution is somewhat in this fashion. So shear stress distribution is in this way along the cross section. Shear stress, I can write the shear stress variation, tau variation with width. This is your width with width. So your equation of that shear stress equals to VQ by IB. It's valid for narrow sections, I would say. If the width is very small, I would say the narrow sections you can apply the shear stress equation. Otherwise, there would be errors in shear stress calculations. Next one is that when we say that the shear force is acting, and when we see the cross section, we say our goal was that because we are dealing about the bending stresses and thereby the development of shear stresses, we said that the load was acting from the principal axis, along the principal axis. We said that the load is acting along the principal axis. So had the load been not along the principal axis, let's say the load is at some eccentricity. Let's say the load is at some eccentricity. So load is not along the axis, principal axis. So we know that because of unsymmetric bending, there is some twisting also. There is twisting. So we can't use that shear stress equals to VQ by IT if there is twisting. If there is twisting, we can't apply this equation. If there is twisting, we want only pure bending. If there was only pure bending moment, there would have been no twisting. Then we can directly apply tau equals to VQ by IT. So you have to take care that if there is twisting, you can directly apply this equation also, VQ by IT. Now we know that we got that differential element. That with the dimensions of that element was, so this was some point A, and the area above that was that we had this small dx, and the depth was d by 2 minus y, and the width was b, and we said that there is some balancing horizontal shear force developed, tau times tau dx, tau bx, tau b dx, and so the shear force here is acting. So if you take that element, I would say along this point A, there's some shear stress acting tau. There's some shear stress acting. So that means we know that from the first chapter, one concept of that shear stresses, that is complementary shear stresses. That's called as complementary shear stresses. So if you have some point A, on that point A, if from one side there is acting shear stress, that means perpendicular to that axis or that plane, there would be one more shear stress developed, that is equals to tau. That is the same value of tau. So if you take that element, now if you want to make that cuboid state of stress, you want to represent the state of stress, that you would say there is some shear stress acting, tau, and there is some shear stress acting. So because of that horizontal unbalanced shear force, because of that unbalanced bending force, you got some shear force F shear, and from that you got some shear stress tau, and based on that you got shear stress in perpendicular direction also because of complementary shear stresses. So that shear stress tau equals to VQ by IT, IB. We can write also BRT, that is thickness of the section, BRT. So we got this one. Now next topic is that now we have to calculate the we have the equation, general equation of that shear stress. Now we want to say for different sections, let's calculate in a separate fashion. So we have that let's take the case 1, that's rectangular cross section. So this is rectangular cross section. So this is some width B and this is some depth D, and there is some neutral axis. This is the neutral axis, and we have the equation of shear stress equals to V A Y bar by I IB. So we have applied some shear stresses. We have applied some shear force on the cross section. We have applied some shear force on the beam. So on a particular point A, we want to say what is the shear stresses here. What is the shear stress here? So we say that get the cross section of BD, and let's analyze that how the variation is along the depth. At this particular shear force of V here, there is some shear force V acting on this section. There is some shear force of V. And I want to say along the depth, how is the variation of shear stresses? How the shear stress varies? So that we are going to check. You write tau variation with the depth. Shear stress variation with depth. So we have some depth of D and B, we have some width of B. Now you want to say you take some point A. So let's take the point A. So this is our point A. So actually the point is somewhere along the long axis. So this is some point A, but because we want to see the effect of that on the cross section. There is a rule of cross section. So we say that there is some point A on the cross section. So that's at a distance of based on the equations we have, that's at a distance of y from the neutral axis. So if we take that differential element of dA dy, then I would say small area is there, dA, that's b times dy, that is small b and dy. And you want to say what is that particular area. Let's say that there is some small shear force of, let's say that there is some V and there is some small area of B into dy. There is some small area of B into dy, and there is the centroid is acting at a distance of, where is the centroid of that particular smaller element acting? That's acting somewhere here. That's acting somewhere here. Centroid at a distance of. So let's say that is your YC. Let's call it as YC. Let's call this as YC. So centroid is at a distance of y plus dy by 2. Yeah, it's wrong. We have the area. That the area. So we are worried about the point A. We got the equation. We are worried about the point A. Okay, this is your neutral axis. So point A is somewhere here at a distance of y. We got the equation from that when we derived that from integration. So we said that there is some point A, and if you take that differential element of dy, so area was small dA equals to y times small dy times b. Then after that you integrated, you got this equation. Now we want to take that area. That's the area is here. The area is here. That is called as area above that point A. Now we can take that directly because your section is constant of constant section. There is no change in the section. So we would take that same value of area that we can directly say it's a rectangle. So I would say the area above that point A, this depth is accompanied with that. So this is some depth of, I would say this depth is d by 2 minus y. Can I say this depth is d by 2 minus y? So I want to take this area above that point A. This area above that point A. So we got that V, and area above that point A, that's equals to B times d by 2 minus y. So we got the area. Now we want to say where is the centroid acting of that particular area. The centroid is acting somewhere here at a distance of y plus d by 2 minus y by 2. Can we say that? The centroid is acting at a distance of y plus d by 2 minus y divided by 2. Can we say that? Centroid is acting at a centroid of that particular area about the neutral axis is at a distance of y plus d by 2 minus y by 2. Yeah. Then we have the neutral axis, that moment of inertia, that second moment of area about the neutral axis, that's BD cubed upon 12. And we have the width. What is the width at that particular point A? So this was your point A. You want to say at that particular location, what is the width of the cross section? That is same B. That is same B. So we got this equation of shear stress. So if you solve it further, you got value of V, and we got some value of V by 12 times V by BD cube. Then we have d by 2 minus y, and we have from this one we have 2y plus d by 2 minus y and divided by 2. So we got this part, and we can calculate that means your 6v by bd cube, and we got d by 2 minus y, and from this one we got 2y minus y, that's y, and we have this d by 2 plus y. So we got this equation, and that we can write tau equals to 6v upon bd cube, and we have this a square minus b square, a square minus b square. That's your equation of shear stress in the cross section of that rectangular cross section, where your value of y is from the neutral axis. So there is y from the neutral axis. So y is from the neutral axis, and maximum it can go up to d by 2. So we can take y from 0 to d by 2. So let's calculate that. What is the shear force at that y equals to 0? That means that equals to 6v upon bd cube, d squared by 4 minus 0. That is equals to 3 by 2 of v by bd. 3 by 2 of v by bd. And we said that we can take this value as tau average, that shear force by area, that we can take as tau average. So we got that 3 by 2 of tau average, 1.5 times tau average. Let's say that along the axis, along the cross section, on the mid span, or we can say on the neutral axis, we got some shear stress of tau average into 1.5 times tau average. That's 3 by 2 of tau average. Then we can say your mid is the neutral axis itself. Tau neutral axis is equals to tau mid, that equals to tau naught, that equals to 1.5 tau average. So we got this part for this rectangle. Now you want to say there is no any other critical section except that the ends. If you want to say what is the value of tau at the ends, so for that you have to take y equals to maximum d by 2. So if you substitute here, that tau equals to that tau comes out to be equals to 6v by bd cube, d squared by 4 minus d squared by 4, that is 0. So we have the shear stress variation of from 0 to 1.5 times tau average, and we have the equation that tau is a function of y square, parabolic variation. So we have the parabolic variation between the 2 points. So we have some parabolic variation. This is some parabolic variation. 2 degree, you can say 2 degree parabolic variation. So we got the shear stress variation along the depth of cross section. So if you want to say what is the location that where the shear stress equals to, at what location that shear stress equals to tau average, shear stress average shear stress, that is v by bd. Now if you substitute the value of that tau equals to v by bd from this equation, you would say what is the location of that while the shear stress is equals to average shear stress. Let's say tau equals to V by BD, that equals to 6V by BD cube D square by 4 minus Y square. So we got this one, BD is gone, BD is gone. So we got this value of 1 by 6, and we got this d square by 6 equals to d square by 4 minus y square. So your value of y equals to d by root 12 or d by 2 root 3. So at a distance of that is 0.28860. That's 0.28860. So you go to some point at a distance of 0.28860. There we have tau average value 0.28860. So this part is 0.5 d, and this is some 0.2886 somewhere here. So there is some. So this distance is that 0. Or we can write in terms of d by 2 root 3. Where your shear stress value is a shear stress value equals to, where your shear stress value is equals to tau average. So you can say this value of shear stress is tau average shear stress, tau average. That's V by BD. And this one is that 1.5 V by BD. So we got this there. So now if you take the circular section, let's talk about the circular section now. Let's talk about the circular section. So there would be some neutral axis, and you want to take some point A. At a distance of y from the neutral axis. You have the equation shear stress equals to V A YC and divided by I neutral axis, and there is the B at that particular location, where B is that width at particular location A, at particular point A, B at A. So because your cross section because your area is varying, area varies with depth. So because your area dA varies with depth, so you can take differential element. In the previous rectangle, we take that element of dy. Then we say that dA equals to small area equals to dA equals to small dy into some area of some width of b. Then I said that we won't integrate it because the derivation was based on the rectangle itself. So we said that there is some value of VAY by IT. But in the equation of circle, you have variation of that area with the depth. Because your area varies with the depth, you can take those differential element. So let's take the differential element above the point A, because we want to take area above that point A, because we want to take the entire area above that point A. That this area we want to take above the point A, and we want to calculate total area, and that it's centroid about the neutral axis. That's our goal here. So main goal of this problem is that to get the value of AYC. That what is the value of area above that point A into it is centroid about the neutral axis. So for that, because area is varying, so we need to take that differential element. So I would say that the value of width here would be some value of b dash. So width at A equals to, I don't know the value of width at A, and I know that the maximum width we can have, that's equals to the diameter, that is 2 times r. So b max I can have, maximum width I can have that 2r. So if you see that, if you say that from the I can make some sort of triangle, can you guess? So you have some element at a distance of y from the neutral axis. Can you make some sort of triangle anywhere such that my width can be calculated, BA can be calculated? So see how want to say what is the variable in this equation. Let's write. So we have applied some shear force on the beam, and your point is some critical point somewhere. Let's analyze it, what we are doing. Let's analyze what we are doing. So you have some beam that's in the form of circular cross section. So you have some beam of length L, and it is simply support beam. Now you have applied some loads, some forces, moments. Yeah, applied some moments also. Now you want to say at a particular point A, at a particular point A, that's at a distance of x, and you want to say what's the shear stresses at this point. So for that you need to take some neutral axis, and you need to take some that point A from neutral axis at a distance of y. And you want to say what is the shear force at that point A. What is the shear force at that point A? Shear force. And let's say the shear force at that point A, that's equals to V. That equals to V. And the area, you can take area. You can take area above. You can take area above or area below. You can take area above or area below that element. Area above or area below. So let's take area above, and you take the y centroid of that area, area above, about neutral axis, and we have that I neutral axis equals to, for the circular case, we have that second moment of area equals to pi d to the power 4 by 64, and your width at A, I don't know, width at A, at point A, I don't know. So for that you have to solve now these 3 points. You need to solve this part and you need to solve this part. So let's solve that. Let's say that we have some radius. If you take this one, can we say this is some radius R? Can you say this is some radius R? So we made some triangle. We made some triangle of that. We made some right angle triangle. I would say this is some radius R. This is some width. This is some depth Y, and there's some B dash. So I can say if I got B dash, then I would say if you multiply it twice, I can get the value of width at A. Can we say that? So width at A equals to 2 times B dash. So your B dash equals to, I would say B dash equals to R square minus Y square, root of R square minus Y square, root of R square minus Y square. So we got the width, and I want to say what is the area of that differential element? What is the area of that differential element? So let's assume that the area is a rectangular area of dimensions that small dy. Let's say the dimensions here we have dy, and the width we have that equals to 2 times R square minus Y square. So can I get the area, small area of that element? Can I get the area of that element? So the area, small area, I can write. So I would write shear stresses. That shear stresses would be equals to, small shear stresses would be equals to V times area above, the area above that point A, the area above that point A. So let's say that in this way. Let's calculate the firstly, let's calculate first moment of area properly. So I have that first moment of area, that Q equals to integral y dA, because your that area is changing with the depth, so we can integrate it. So you have to take that, you have to take the limits from that y to r. You have to take the limits from y to r. So your point A, see from the cross section, your point is at a distance of y, and you have to go maximum to the distance of r. You have to go to the maximum distance of r, and you want to take this area where your limits are from y to r. So you take limits from y to r. Your limits are from y to r. So you have to integrate it, and we got a small differential area also. This is your differential area. That means your Q value equals to integral from y to r y into dA. Value of dA equals to 2 times root of r square minus y square and dy. So we got this first moment of area, and you need to solve this one. How can you solve this? Y into 2y. So we can substitute something. Let's substitute some stuff, that r square minus y square is some sort of, let's say that equals to some x square. Let's say that equals to x square. So if you differentiate it, I would say that is equals to 2y dy equals to 2x dx. So we got this 2y dy equals to 2x dx minus times, And we have one more thing that now you take the limits because your variable changes. So I would say for if you go for y from y to y, if you go from y equals to y, and your x square goes from r square minus y square. That means x goes from r square minus y square and whole root. And similarly for y equals to r, if the y goes from y to r, then we have x goes from r square minus r square, that is 0. So your limits are from, we can say limits are from, so limits got changed from root of r square minus y square to 0, and you got 2y dy equals to minus times 2x dx, and you have substituted the value of root of r square minus y square equals to x. So you got this function now. You got this function that says that is minus times 2x square by 2x square dx integral. So we got value of minus times 2x cubed by 3, and the limits are from 0 to, or we can say root of r square minus y square to 0. So we got this equation, then we can say total value of 2 by 3 of r square minus y square over 3 by 2. So we got this value of first moment of area about the neutral axis. We got this area of the first moment of area about the neutral axis. Okay. Now what is the next setup that we can have? So we got the area, first moment of area. Now we can solve that. We can solve for the shear stress. So we got this one, and we got also that first moment of area equals to 2 by 3 of r square minus y square, r square minus y square power 3 by 2. And similarly we have the moment of inertia about the neutral axis, that was pi d 464, pi d power 4 by 64. And we have that b at a, that width at a equals to 2 times b dash, that is 2 times root r square minus y square. So we can write that 2 times root of r square minus y square. So if you see this, so you have this one, r by 3 by 2 minus of 1 by 2, that equals to 1. Then that means we are left with 2 by 3 into 64 here, and we have pi d 4, and we have r square minus y square and divided by 2. So we got this one. And if you take that diameter in terms of radius, so we can solve that also. So diameter equals to 2r. So similarly your d4 becomes 16r. So this goes, and 16 into 4, I would write this as 16r power 4. So 16 ones are 16 fours are. So I got value of 4 by 3 v r square minus y square by r square, and we have one more thing, that's pi. So we got this value. Now if you want to take in terms of average, I would say your shear stress average equals to v by area, v by pi r square. So if you write in terms of the average shear stress, I would write v by pi r square, that it means tau average, and we have that, let's write it in terms of r square into r square. So I got tau average, then we have r square minus y square by r square. So that means 4 by 3 tau average 1 minus y square by r square. So this is your final expression. That shear stresses along the cross section of circular cross section varies in this fashion. So parabolic variation y square. So let's substitute the value. Say this was your cross section. Let's say this was your cross section, and I want to say what's the shear stresses, how is the shear stress varying with the depth. So this is some neutral axis, and this is the top, and this is the bottom. I want to say how is the shear stress varying with the depth. Let's substitute the value of y. We know that y is from neutral axis. This is neutral axis. Let's say the value of y equals to 0. Let's substitute the value of y equals to 0. So I would write tau at mid is equals to tau at neutral axis. And that would be tau max. That would be tau max. That is equals to 4 by 3 into tau average. Because y is 0. So we got 4 by 3 tau average. 4 by 3 tau average. This is some value of 4 by 3 tau average. And at the end, if you substitute the value of y equals to r, at y equals to r, your value of this one becomes 1, so your shear stress becomes 0. Tau at end is becomes 0. So you got the shear stress is equals to 0. So here we have 0, we have 0 here. So there we can say this is parabolic variation. There is some parabolic variation. I want to say at what location we have tau average, that shear stress equals to tau average. At what location? I would write tau average equals to 4 by 3 tau average 1 minus y square by r square. So I can get a value of 3 by 4 equals to 1 minus y square by r square. So I can get value of that 1 by 4 equals to y square by r square. That means y is r by 2. At y equals to r by 2, you have shear stress equals to tau average. Y equals to r by 2. So at y equals to r by 2, so this is r, this is total r. You need to go to distance of r by 2. Then there we have shear stress of tau average. At y equals to r by 2. From the both sides equal to r by 2, you have shear stress variation. That tau average value of shear stress equals to tau average. Thereby you can join by parabolic curve. So this is the shear stress variation. Let's take the third problem that we have cross section of that triangle cross section. We have triangular cross section. Let's take the triangular cross section. Let's take the cross section that is triangular cross section. So we have the neutral axis at, let's say the total height is h and width is b maximum. So I would say the centroid would be at h by 3 from the top. So this is neutral axis, or this is centroidal axis. So distance of h by 3. That means this part left over is equals to 2h by 3. So you want to take any point. Let's take any point. Let's take any point A. So this point is at a distance of y from the neutral axis. So this point is at a distance of y from the neutral axis. So we have the equation that shear stress is equals to V A y bar or yc, y centroid of that area, and divided by I neutral axis into width at that point A. Width at that point A. Now, what's the area? That area we have to take. We can either take above the point A, or we can take the area below the point A. If the point A is here, if you take the area above, so you have to take this area. That's very tough calculation, I can say. That takes time. And if you take this area, that's very simple to calculate. So which one is easier for you? Which one you would prefer? Which area you would prefer to take? Which area you would prefer to take? That area above or area below? It's up to you. I would prefer smart calculations. I would prefer that you go to the area below. You would take the area below. If you take area below, so we take area below. So I would write here area below. Let's write that we can take area below, and at the centroid of that area below, about the neutral axis, neutral axis. So this is the first moment of area about the neutral axis. But the area is above the area should be below the neutral axis. Area should be below the neutral axis, below the point A. Yeah. So we have to take this area now. We have to take this area now. So this is point A here. So what is the depth we are left with? What is the depth total we are left with? So you go to some point A at a distance of y. So the left over would be equals to 2h by 3 minus y. Okay, and there is some width BA at that location, BA. This is some width BA, and I would say there is some centroid of that area somewhere here. What is the distance of that centroid from the neutral axis? Can you calculate that? YC bar. So this is neutral axis. So the centroid would be at this distance of YC bar. So YC bar equals to, or YC equals to, I would say that equals to, firstly it is up to this point, that equals to Y. Then after that you have the centroid of the triangle at a distance of 1/3. So I would write 1/3 of that distance of that height of 2h/3 minus y. So you got the centroid. Y plus, so this is the centroid, that y plus 1/3 of this height, 2h/3 minus y. So you got the centroid. And area, what is the area of that particular area below the point A? Area below the point A, that is 1/2, and width at that location, and 2h/3 minus y. Height is total of 2h/3 minus y. Let's keep the width as it is. It might get cancelled. It might get cancelled in the calculations. Let's keep the width as it is. Let's keep the width as it is. BA. So you have to substitute the values here. Let's substitute the values here from this side. So I would write shear stresses equals to, tau equals to V. Value of A, area below I can take 1/2 B at A and 2h/3 minus y. And the centroidal distance is at y plus 1/3 of 2h/3 minus y, and divided by the second moments of area above the neutral axis. So that equals to, we know that that value equals to bh³/36. So that equals to bh³/36, and the value of y and the value of width at A, and we have to take the width at A. So if you take the width at A as it is, so this would get cancelled, width at A. So we have to calculate now this part. So let's calculate that. So we get that we got this value of V/2 into 2h minus 3y/3, and we got this value of y plus 2h/9, minus y/3. So we got this part from the top, and we got from the bottom bh³/36. So we got this equation. But shear stress equals to this equation. Shear stress equals to V/2 2h/3 minus y, that extra. Now what we can do? Let's simplify it further. Let's simplify it. So we can write 36/2, that's 18. 36/6, that's 6. So 6v into 2h minus 3y, and we got this one, 3y minus y/3, that's 3y minus y, that's 2y/3. That's 2y/3 plus 2h/9, and divided by bh³. So if you solve this part, so we got this one, that 2h into 2y/3. Let's take the 2/3 common. 2/3 common. So we can get the value of 2/3 common here, and we can calculate. So that calculation is easy. So I would say 2hy minus 3y square plus 2h square/3 minus 3yh/3. And we have 2 times, and we multiply that 2/3 and bh, 2/3. So if you solve that further, you get a value of 3 to the 6 4v/bh³, and you got this value of 2hy minus yh, that is hy, and this one 3 3s are 9, 3 3s are 9. Let's solve this. Yeah. So we got this one, 2hy plus 2h squared by 3 minus 3y squared. Do we got this one? 4h squared plus 9y squared. 4h squared. Let's see whether we have the correct equation. Let's see. Let's check it from the values. So if you say let's say that we got this value of shear stress. Let's say we got this value of shear stress. Let's apply that in the cross section. So we had that cross section. We had this cross section. We had this cross section. We had this cross section. I want to say whether the calculations are correct or not. Neutral axis, mid. This one is h by 2, and this one is h by 3. This is neutral axis. This is mid. I want to calculate at ends, at the mid, and at the neutral axis. So these values I have to substitute here. So, but the value of y is from neutral axis. So this is the location where y is from. So y had to take from neutral axis. So for the calculations at neutral axis, you have to substitute value of y equals to 0. So you can write tau at neutral axis equals to, that means y equals to 0. So you substitute the values, you get 4b by bh cube, and first part is your, third part is your, you got value of 2h squared by 3, 2h squared by 3, 2h squared by 3. That means 8 by 3. So you got a value of 8 by 3 v by bh. 8 by 3 v by bh. Do we got this value? 8 by 3 v by bh. And if I want to take in terms of average stress, we know that average stress equals to shear force by area. And the area of the triangle, what is the area of the triangle? bh by 2, bh by 2. So this is the area. And if you want to take in terms of that, so if you divide this one divided by 2, then that means you have to divide this part also divided by 2. So that means your value becomes equals to 4 by 3 tau average. So your shear stresses at neutral axis is 4 by 3 tau average. So your shear stresses at neutral axis equals to 4 by 3 tau average. So that is 4 by 3 tau average, where your tau average equals to v by bh, or we can say v by bh by 2. v by bh by 2. Now you want to say what is the value of shear stresses at the mid location. That means at y equals to the difference of, so tau at mid equals to at the rate of y equals to h by 2 minus h by 3. So this difference of y, h by 2 minus h by 3, that equals to h by 6. So you have to substitute value of tau y equals to h by 6 here. So if you substitute here value of y equals to h by 6, so you got a value of h into h by 6 plus 2h cubed by 2h squared by 3, 2h squared by 3 minus 3 into h by 6, that is h squared by 36. So 3 by 36 negative plus 2 by 3 plus h 6 inverse 3 by 4 into 4, that is 3 times. So we got a value of 3 times that. So we got a value of 3v by bh, 3v by bh. And in terms of average, if you want to take in terms of average, I would write 3 by 2 v by bh by 2. So we got a value of 3 by 2 times tau average. 3 by 2 times tau average. So we have value of 1.5. Value of 1.5. If this is 1.33, and second one would be 1.5 tau average. So then after that, you can join by a parabolic variation. This is parabolic variation, that at the mid you have maximum. So shear stresses is mid, at the mid is maximum. Similarly, for the rectangle, you had maximum shear stress of 1.5 tau max, 1.5 tau average at the mid span. Similarly, for the circular case, you have maximum shear stresses at the mid, that was 4 by 3 tau.